Hello! Today I'm going to talk about a question that has come up, and that question is, why does the resistance or impedance of a power source appear in series with that power source? Now this isn't something we're likely to encounter in electronics technology or probably even engineering. Maybe if you're giving a lecture on physics you may need to deal with it, but when we're dealing with electronic circuits we usually simplify things and don't deal with these deep subjects. But sometimes people get hung up on things they don't understand and can't move on until they resolve them. And I've seen electrical engineers and even physicists get hung up on this particular concept. So let's take a look at this and find out why the resistance or impedance of a power source appears in series. So let's start out by imagining that we have a wire. We don't care how long it is or how much resistance it has at this moment, but next to it we have another wire and a battery in series with it. And I'll put a switch here so we can energize that at will. And what we're going to do now is close that switch. And so what's going to happen is we will get a current in this wire. And what happens when we put a current through a wire? We get a magnetic field. So a magnetic field is going to build around that wire, and this other wire is inside that magnetic field. So as that magnetic field builds, it's going to have an effect on that wire. And what's that effect? Well, it's going to cause a current to flow in that wire. Now, what causes that current? We're going to start taking a little deeper look at it here, because according to Faraday's law, that changing magnetic field induces an electromotive force in this wire. And we're going to represent that electromotive force with this little cursive E. That may be new to you, but in physics we differentiate between an electromotive force such as this one created by that changing magnetic field and voltage. There is a difference. I have a video talking about that linked in the description below and maybe up here if I can do that. But we represent that particular type of electromotive force which can exist in the absence of a voltage differential. We represent that with the cursive E, sometimes represented with just a lowercase EMF. But we'll just leave the cursive E there for now. So there is an electromotive force that is pushing electrons in this direction in the wire. Now in this class, like almost all of the electronics industry and academia, we use conventional current. So I don't want to be switching back and forth between following the electrons and the conventional current. And fortunately we don't have to, because even though it's the electrons that are moving here, if we take a little look here and imagine we have a golf course here. This is the green at a golf course, and there is the hole that we're going to put our golf ball into. We put it into the hole and move on, don't think much of it. But then the groundskeeper comes along and he moves that hole. Why? Well, because they don't want everybody always over here. It's going to ruin the grass, so they move that hole around to keep the green in good shape. So the groundskeeper moved the hole over to there. So the hole moved from there to there. Did it? No. The groundskeeper came in and took a plug of grass and dirt from here and moved it over there. The hole didn't move, the grass and dirt moved. But it sure looks like the hole moved. So when it comes to electronics, the electrons and the positive charges do the same thing in this wire. If we could see those electrons, as we watch them move down, it would appear to us that positive charges were moving in the other direction. So let's follow those positive charges instead, and we can stick to conventional current. Let's get that symbol out of the way. So positive charges are moving in this direction, and if there was a wire continuing on, assuming that there was no impedance out there, no resistance, just superconducting wire, that current would just simply move on and nothing special would happen. But because this wire comes to two abrupt ends, those moving positive charges can't go anywhere, so they're going to pile up on this end of the wire. I'll just represent those with some little circles. And down here, the positive charges are going to be pulled away from that end. So if I try to draw a gradient here, I'll show that they get closer and closer together so that we have a gradient of density of positive charges becoming more dense up here than down there. Now what's going to happen when we push those positive charges together? Well, what happens if you take some air and push it into a container? Those air molecules are going to push against each other and push back, and you're going to get some air pressure. And if you push them closer together, they're going to push on each other harder, and you're going to get more air pressure. Well, the same thing is going to happen with these charges. They're going to be pushed together, they're going to repel each other, and they're going to push back, and we're going to get electrical pressure that we call voltage. So we're going to get a higher pressure up here where the positive charges are pushed together, and a lower pressure that we label positive and negative. Remember that positive and negative voltages are not the opposite of each other, but a negative voltage is just a voltage that is lower than some other voltage. So higher voltage positive, lower voltage negative. And so now we do have a voltage differential between the ends and a gradient along the wire. So if I put a voltmeter out here, I can measure a voltage. Now what we're going to have to do here is freeze time, because this is going to happen almost instantaneously, and when that magnetic field stops getting stronger, it's going to build up and then stabilize. When that stabilizes, it's no longer going to have an effect on this wire. It only affects it while it's changing. And so this whole thing will go away. So we're going to freeze time and just look at this at a moment in time, and let's say we have, at this moment, 1 volt across this wire. That also tells us that our electromotive force, because the voltage differential we get at the ends of those wires will be equal to the electromotive force. This sort of reminds me of Richard Feynman's lecture where he talks about alternating current, and he shows a generator which he has as just a coil of wire, and there's either a spinning magnet out here, or that wire is spinning in a magnetic field, and that wire is going to have an electromotive force in it, which is going to cause a voltage across there. So notice that as a physicist, he differentiates between the voltage differential and the electromotive force in the wire, exactly like we are doing right here. So there is a voltage, and we decided that that voltage at this moment in time is 1 volt. Now let's say that this wire has 1 ohm of resistance. So now we have something that's generating an electromotive force causing a voltage differential. How is that resistance going to be seen in there? Well, let's get this out of the way and take a quick look. Get rid of our little gradient of charges here just to clean things up. So we've established that our wire, that's becoming a little bit raggedy here, there we go. We've established that wire has 1 volt across it and has 1 ohm. So could that ohm be in parallel? So where is that 1 ohm? Let's erase that there for now. Is that 1 ohm of resistance in parallel with the wire? Is it in series with the wire? Is it neither, or is it both? Well, let's look at what happens if we see it as being in parallel with the wire. Well, this is where some people run into trouble, because let's just get this out of the way for a moment. They see that there's 1 volt across that wire, and that wire has 1 ohm of resistance. Therefore, it should have 1 amp of current flowing in that direction. And because they don't understand the nature of electromotive force, they think that this acts as if a voltage is being applied externally, not being produced inside the wire. And so they see the 1 volt and they think there should be 1 amp flowing through there. Well, then they think, well, what if this happens to be 0 ohms? Well, if I can't have a voltage across 0 ohms, therefore that voltage must not exist. That's one of the explanations I've heard, is that you can't have a voltage across there. Well, let's find out if that is true. So why is this voltage here in the first place? It is not being applied by an external source. It is actually developing in that wire. This wire itself is the voltage source. Why is that voltage there in the first place? Because there is a changing magnetic field developing an electromotive force that is pushing our charges in that direction. So This resistor is also inside that magnetic field, so that means that in the resistor we have an EMF pushing charges in that direction. So maybe we would have this resistor in parallel, except there's an electromotive force that is blocking current from following this path. So there is no current path through this resistor. We'll just break that path because it's being blocked. So the whole reason we have this voltage is because the electromotive force is pushing our positive charges that direction, taking them away from this side, giving us a positive to negative voltage. And if this resistor is in parallel, that electromotive force is pushing them the same way, so we cannot have flow through that resistor. So it can't be in parallel. So we've established that. So now let's take another step here. So there's our wire. We'll take out this wire over here and just remember that there is an electromotive force over here. And let's say it's equal to 10 volts now. So there's an electromotive force of 10 volts pushing current in this direction, and what we're going to do now is hook up a wire to it and put a resistor over here. Now just to simplify things, we're going to do like we usually do in electronic circuits, and our connecting wires we're going to assume have no resistance. So these wires have no effect on the circuit, which will simplify our view of what's going on here. And let's make this a 9 ohm resistor. So we have an electromotive force of 10 volts in the circuit, and we established that this is 1 ohm over here. So we have a series circuit, don't we? There's only one possible current path. The definition of a series circuit is one current path. There it is. And we know there's 10 volts of electromotive force in there. And can we measure a voltage across this anymore? No, because those charges are no longer backing up here. They are continuing on around the circuit. So for the time being, let's forget about that voltage. We're going to come back and see what's actually going on there in just a moment. But now we know that there's an electromotive force of 10 volts pushing current in this direction. What's our total resistance of this series circuit? 9 ohms plus 1 ohm. So our resistance equals a total of 10 ohms. Our voltage, which is electromotive force, equals a total of 10 volts. So according to Ohm's law, what should the current be? We should have 1 amp of current in there. So there's our 1 amp of current. Now what's going to happen when that 1 amp of current encounters this resistor? Well, where conventional current enters the resistor, we get a backup of charges, so we get a higher voltage. So we're going to get a higher voltage here. And our charges are being pulled away from the other side. In fact, it's just like it was before. This is pulling charges this way and pushing them that way. So those charges are being pulled away from here. So there's fewer charges and we have a negative voltage. And what's that voltage going to be? Well, we have 1 amp going through 9 ohms. Therefore, we are going to get 9 volts. Okay, so the current is going to continue on around the circuit. And what's going to happen when it encounters this wire here, which has 1 ohm of resistance? Well, once again, we have our conventional current encountering the resistance here. We're going to get a backup of charges at that point. So we're going to get a higher voltage here, and we're going to get a lower voltage there. And notice that the polarity is reversed from what it was when the circuit was open. Remember, these wires, we're assuming, have 0 resistance, so we don't have any losses along these wires. So what voltage do we expect across this 1 ohm resistor? Well, we have 1 amp going through 1 ohm. It's entering here, so we get a higher voltage there. We'll put a little voltmeter out here. And we expect 1 amp, 1 ohm. We expect 1 volt. Now, does this work? Does this satisfy Kirchhoff's voltage law? I think there's a problem here because we have some voltage. Let's start here. We have 0 volts here. We add 1 volt. Add 9 volts, we have a total of 10 volts, okay, but Kirchhoff's voltage law says our total voltage should be 0, but this says our total voltage is 10. So this violates Kirchhoff's voltage law, doesn't it? Actually, no, because we're still not properly accounting for what this electromotive force is going to do. Now, we can't measure that directly. We can only measure it when the current pushed by that force encounters resistance and develops a voltage differential. Then we can measure that, and that voltage differential will equal our electromotive force. So let's see, where is that electromotive force? Well, it's inside this wire. Well, let's Let's put it in there. Let's divide this wire in two. Get rid of some of this clutter out here. So I'm going to divide that into two resistors, and let's see if this works. So there's resistor 1, there's resistor 2, and we'll put a source of EMF right in the middle. 10 volts of EMF. Okay, let's look at our currents again. We have our current flowing into here, causing us 9 volts. Currents flowing over to here, and we see that there's going to be a total of 1 volt across that resistor. Let's not look at that just yet, but we do have 10 volts of EMF pushing conventional flow in that direction. And what's going to happen to that conventional flow? It's going to encounter this resistor right here. So we're going to get a backup of positive charges. So we get some positive voltage there. And we're going to be pulling charges away from here. So there will be a negative voltage there. How much will that be? Well, how much is our electromotive force? It's going to be 10 volts. So let's put a little voltmeter out here and show that now, because the electromotive force, which cannot be measured with a voltmeter, is pushing current, encountering this resistance here and backing up, giving us a positive voltage, and that's being pulled away from this resistance here, giving us a negative voltage, and the total voltage will equal the electromotive force. There's our 10 volts. So we have 9 volts over here, positive to negative. Let's put these voltages back. So that voltage there is going to be, well, it's a half an ohm now, as is this resistor. So now it's only half an ohm. We're going to get 0.5 volts. What's the polarity? The current is flowing this direction. So where the current encounters the resistor, we're going to get there's already a positive voltage there. And where it exits, it's going to be negative. And where the current encounters this resistor here, we're going to get a positive voltage. And where it exits, and there's already a negative symbol there. So the voltage across here is the opposite polarity. Look at that, positive to negative, negative to positive, positive to negative. They're opposite each other. Is this going to satisfy Kirchhoff's voltage law now? Let's take a look. Let's start right here. Call that 0. We're going to gain 10 volts. I'll just put the number 10 there. We're going to gain 10. Now we reverse the polarity. We're going to lose 0.5. Now we're going to come over here, and we're going to lose 9 more. Then we're going to come around here. We're going to lose 0.5 more. And lo and behold, our loop has 0 volts. So it does satisfy Kirchhoff's voltage law. And let's take a look at something here. Now remember, this whole entity, getting awfully cluttered here. Let's erase some more stuff just to keep things simple. There we go. Now remember, this whole entity is that one piece of wire. So we'll circle that just to remind ourselves that that is the entire piece of wire, or the secondary of a transformer, or the winding of a generator, whatever it is. And it's all in one piece. And so we have 10 volts of electromotive force, and we subtract 0.5 volts there, subtract 0.5 volts there. So remember, we started with 10, we lost half a volt, lost half a volt. So the total voltage across there is going to equal, start with 10, we lose 1, we have 9 volts. Is that starting to look familiar? Well, it's starting to look like our model of a battery. So if we change this to a battery, we model our battery as a voltage source with a resistor in series. Now once again, I'll circle that because that's all one entity, 10 volts, 1 ohm, and we've determined that there's a total of 10 volts and 10 ohms, and so there's 1 amp of current. Does this all work well? Let's see, 10 volts. We start out with 10 volts. We're going to lose 1 volt, positive to negative there. So the battery's that polarity. So we start out with 10, we lose 1 volt, have 9 volts left over. That 9 volts is across here, and everything balances out. 9 ohms with 1 amp through it, we get 9 volts. So that looks like that. So it seems to work. In fact, really, When we model a battery, like I said, in electronics, we tend to ignore some of these deep subjects, but the proper way to model a battery should be, look at that. It should be a source of EMF in series with a resistor. So now we've got 10 volts of EMF, 1 ohm of resistance, and there's our proper model of a battery. And where does this EMF go? As long as these resistors are in series with each other, and this is in series with everybody else, it doesn't really matter. So we did have this. I'm going to keep that 9 volts there. We had our EMF here, and our resistances here, or impedances, or whatever they happen to be. And with those one above and one below, we get our 9 volts out. Or if we simply move the resistors into one place, just simplifying the circuit, it works just the same. So in the end, we find that we can take that total resistance of that wire and the total electromotive force, put them in series with each other, and everything works out. Now, I'm not sure if that really clarifies why that has to go there, but it does clarify that if we put it there, it does work. So is this resistance in series, in parallel, both, or neither? Well, it depends on the way you look at it, but we look at it in parallel, that didn't work because the electromotive force was pushing the current the other way. So it could be in parallel, but because of the nature of the circuit, having this electromotive force pushing, that path was blocked. Therefore, we have to find another way to model it, and we found that if we model it in series, it works perfectly well. And also, I pointed out that a battery also has electromotive force in it. It's chemical instead of electromagnetic, but it's the same thing. We have an electromotive force in here that is pushing current, and we have a resistance in here, and it works out the same way. This could be a battery, or the secondary of a transformer, or the winding of a generator. All of them work the same way, and we find that our resistance goes in series. And when we have AC circuits, the impedance would go in series also. So there is why the resistance appears in series. It can't appear in parallel because that electromotive force is blocking that path, so it must be in series. And we put it in series, and lo and behold, that resistance works out just fine. So we did have a wire. I'll try to draw as a nice thick line there. I'll double that just so we can see what we're doing here. That had 1 ohm of resistance. That's over the total wire. It had 10 volts of electromotive force, and that was all through the wire. But when we combine them, we find that we can put that electromotive force in series with the resistance, and the circuit works. And that's basically what Georg Ohm found out, that caused Georg Ohm to have the ohm named after him, because those before him had failed to understand the nature of resistance and electromotive force. And that includes Andre Ampere, who the amp is named after. He didn't understand this and even denigrated Ohm for saying that that's the way it worked, but he proved it did work, and that's why the Ohm is named after him, because he discovered that the inherent resistance in your power source, and in his case it was thermocouples, must be placed in series with the power source for this circuit to work. And he worked out his Ohm's law. That's been modernized, but worked that out to give us Ohm's law, which is now called Ohm's law because of what he did. So I hope you found that useful and informative. And if you did, please give me a thumbs up down below. It really helps the channel. And if you would like to study electronics technology and perhaps become a certified electronics technician, or just get a jump start in your studies in electrical engineering, you can take my free course on electronics technology at Vocademy.net. Just go there, sign in, take the course, and everything's 100% free. And a big thank you to my patrons at Patreon. I could not make these videos, and I could not support Vocademy without your help. And to help me put these videos online and to help keep Vocademy free, you can go to patreon.com/Vocademy and pledge your support. Or look in the description below there for a link where you can make one-time donations. And so again, a big thank you to my patrons, and thanks to everyone for watching.